Okay, so we'll be using that principle of superposition presently, but right now I need a new idea, wave fronts. So let's return to our picture of electromagnetic radiation or light. Here's the x-axis, the y-axis, and the z-axis, and let's consider, as we have been, light that has electric field pointing along the plus and minus y-axis. I'm going to draw 1.5 wavelengths worth, so the electric field vectors go like this, and again I'm only plotting the electric field along for points along the x-axis, but remember this is a plane wave, and so let's say if I were to consider some other point at the same value of x here, the electric field would have the same magnitude and direction there. So the magnetic wave is in phase with this, but points along the plus and minus z-axis. So it looks something like this, with the field vectors like so. We define the wave front to be the point of maximum electric and magnetic field. So for this plane wave, this point would be a point on the wave front, and the wave front would actually be a plane, an infinite plane perpendicular to the x-axis, like this, that intersects the x-axis here. And here would be another wave front, and there'd be another plane perpendicular to the x-axis that intersects the x-axis at this point, where the electric and the magnetic fields would be maximum. So I now want to view the same picture but looking from above, so looking down along the y-axis. So here is the x-axis, and here's our first wavefront there, and here is another wavefront, and both of these are propagating to the right at the speed of light. Okay, now let's add into this a new idea called Huygens Principle. This is named after Christian Huygens, who was the first person to theorize that maybe light was a wave. And what he said was you can consider each wavefront to be made up of an infinite number of point emitters of light. So let's say on this wavefront there would be an infinite number of little points, each of which is emitting light in like a sphere coming out of it. So this one is emitting light that comes out in a sphere, and then just for graphical clarity I'm going to use green for this one. It's emitting a sphere that's centered on that green point, and here's a red one that's emitting a sphere that's centered on that. And so when we superpose the light coming from those point emitters, that leads to the formation of the forward propagating wave front. So one can show, although it's beyond the level of our course, that Huygens' principle is consistent with Maxwell's equations. So now let's combine these ideas to look at the experiment of two-slit interference, which was first conducted by Thomas Young in 1801. We're going to use the same viewpoint that we had here, where we're kind of looking down along the y-axis. And here are some wavefronts for a wave that's propagating to the right. And this wavefront is just about to hit a barrier. In a perspective view, the barrier would look like this. So this part is opaque, and then there's a little gap, and then another opaque part, and then another gap, like that. So these two gaps are called slits, And in this view, so again, we're looking from above down onto this, the barrier would look like this. There would be this first part here, and then the first gap or slit, and then this middle part, and then the second gap or slit, and then the rest of it, like so. So if we apply Huygens' principle to this, we can see that a point like this that's trying to emit is going to be blocked by the barrier. However, this point here, when it reaches the barrier, can emit, and so it's going to emit as each new crest comes in. We will emit, each new wavefront comes in, will emit new wavefronts coming out of this, spreading out in a spherical pattern centered on this point. Similarly, when this point emitter gets here, it will emit a new wavefront, and correspondingly when this one behind it gets there, it'll emit a new wavefront. And so there will be a series of spherical waves centered on this bottom slit, spreading out from that. And we get this fairly complicated pattern, which I haven't drawn particularly well. In particular, the distance between the wavefronts here should be the same as the distance between these wavefronts. But we can still use this to understand qualitatively what's happening. Remember that the total electromagnetic field in this region will be the superposition of the waves being emitted from these 2 point sources. And so that means at a place where the wave fronts intersect, like this place, there we're going to get a very large wave because we're superposing. If I were to try to graph the black wave and the green wave, at that point they're lining up, and so they're adding up nicely to give us a really big wave. On the other hand, if we go to a point, let's say here, where we have the wavefront of the black wave halfway between the wavefronts of the green waves, then that would be a case where this is at a maximum for the black wave. So here I'm plotting, let's say, electric field versus position. So at this point, the black wave is at a maximum, but because we're right in between the wavefronts for the green wave, it would be at a minimum. And so they're canceling in this case. So if we add these together, I get 0, whereas in this case where they're lined up, I add them together, I get something that's twice as big as what I started with. So when they cancel, that's called destructive interference. And when they add together nicely, that's called constructive interference.